steps for finding mean, standard deviation, variance, all that stuff on your calculator. Punch these into the calculator and we'll find the standard deviation, all that stuff. And you just have to be careful when you're punching in. This right here shows what it's going to look like on the TI-83 or 84. That's what we'll use most of the year. Remember your X bar is your mean. This tells the sum of all the X's. The S tells the standard deviation if you're dealing with a sample. And then the sigma tells the standard deviation if you're dealing with a population. It's got the number of items in the set that you're dealing with, and if you scroll on down, it's got more things, like it'll tell you the median, tell you the highest number, the lowest number, so that you can find the range, etc. Some key things: standard deviation's always got to be greater than or equal to 0. Standard deviation, measure variation, the values of the mean. Larger the S is, the more the data varies, so the more spread out the data is, the larger the standard deviation is. Standard deviations in the same units as the original units. The value of the standard deviation can increase dramatically if you have outliers. It sort of goes over the same thing. If you look in here, notice standard deviation 0, because they're all the same. When you have something that's sort of symmetric, there, got a sort of low standard deviation, but your X bar, your mean's still the same. Here the mean's 5, but your standard deviation's bigger because the data is more spread out. These are the symbols, all the different symbols that we're going to use. Notice you have symbols for population, and you have symbols for sample. We'll probably be doing the sample more than population, but standard deviation, spread. There's 3 basic rules that we're going to talk about today. Range rule of thumb, empirical rule, and Chebyshev's theorem. Chebyshev's works for all data. The empirical rule only works if it's symmetric, and the range rule only works if it's an estimate. 3 rules we're going to talk about. Range rule of thumb, that's just an estimate, something you can do dealing with standard deviation. The empirical rule is the one, this one's the one that, my stuff would work right. The empirical rule is the one that we're going to use most of the year, but it only works if the data is symmetric. And most data does come out to be symmetric, and sort of symmetric at least. And that's a lot of times what we'll do with data is we'll make it so it's a little more symmetric as we go, so that we can use the empirical rule in different steps. Chebyshev's theorem works for all data, so that would work for any kind of data, whether it's symmetric or not. Again, the range rule, we'll talk about it in this chapter, then I don't think we deal with it a whole lot the rest of the year. This is just, if you got some kind of job that deals a lot with statistics, you might use the range rule just to get an estimate every time, so you wouldn't have to go through and do all the calculations for every set of data. All right, the range rule. With the range rule, remember range is just high minus low. to give an estimate of the range, you could do 4 times the standard deviation. So if you know the standard deviation, you just take 4 times that, and that would tell you the range of the data, even if you don't know the whole set of data, even if you don't know the highest and lowest, you could get some idea how far out they go. And to give an estimate of the standard deviation, you do just the reverse of that, and you take the range divided by 4 if you do know the data. So on some of the data that we had, you know, maybe you knew the highest was 22 and the lowest was 7. You just take that, subtract, you get 15, divide that by 4, and that's going to give you an estimate of your standard deviation. Give you an estimate of what S would be. It's not exactly what S is, but it's fairly close. We talked about this one last time. Sample woman's heights has a mean of 64, so we know that our X bar is 64. Standard deviation, our S, is 2.5. Using the range rule, most women fall within what heights? So we could find the range by using that. If we go back to this, and we did this last time, I know, if we go back to this, we know the standard deviation this time, so all you're going to do is take 4 times 2.5, and that gives you 10. So you're saying most women fall within 10 of that mean, of that X bar, all right? Now where you got to be careful at when you're doing that is they said the mean was 64. Well, we want to be within 10 of that. Does that mean I go up 10 on this side and down 10 on this side? That'd be 5 and 5, because if you go up 10 and down 10, then all of a sudden you made your range how much? 20 instead of 10. So you go down 5, which would be 59, and up 5, which would be 69. So we can say that most all normal women fall between 59 inches tall and 69 inches tall. Does that sound about right? What is 69 inches?
5'7".
5'7"?
Yes.
I don't know, is it?
I'm gonna guess that is
Because 5 times 12 is what?
60.
5'9". So we're saying about 5'9" to what's 59? 4'11". Does that make sense? Most women fall in between those heights. Yeah, you don't see a whole lot of women that are 5'11", 5'12", or 5'12", 6 foot, anything like that, right?
my aunt is
4'8". So she would be a outlier on this, right? She'd be out a little bit. I know my mom was probably about 4'9" or so.
When I was little, I used to stand next to her because I felt big.
We talked about this one last time. Sample exam scores used in a class handout had a mean of 73.6, which again, this is your X bar right here then. 73.6, which of the following is most likely the standard deviation is of the sample. So we're trying to figure out which one's most likely the standard deviation. This time, we don't know any of the other stuff, so if we're just looking for the standard deviation, we had that formula that said S equals the range divided by 4. Well, we don't know exactly what the range is this time because they didn't tell us the highest and lowest scores. But if we went through here and looked at these, first one, is the standard deviation going to be that? Our most score is going to be 74.5 away from 73.6. That doesn't even make sense because that's going to put us in the negative. Now, when I grade your test, sometimes, Sean, I think some of you owe me some points, so you're in the negative, but you know I don't ever get negative scores, right? So that one will work. 12.8. We look at 12.8. If we go couple below, couple above, that's about 13, let's say. So that'd be 26 below. And if we go, let's just make that 74. If we go 26 below that, what's 74 minus 26? Like 48. So 48 to, if we add 24 or 26 up, 26 up would be 100, is that right? Now, is that feasible that all the scores would fall in between there? Yeah, maybe. Where'd I get? 26, because I just took this and I said, all right, that's close to 13, just making an estimate. So 26 would have been double that. Oh, we shouldn't have did double that, should we? You're right. Not double that, what should it be? Should be times by 4, so 26 double that, that'd be 52. Now that's wrong then. We go down 52, we're at what, like 22? We go up 52, we're at 126. There, that looks better. Is 12 gonna be the standard deviation? Now, are we expecting that all the scores are gonna fall within that range? Yeah, but if we're gonna be that far off, we could have just said, well, all the scores are gonna fall between 0 and 1,000. Are they all gonna fall in there? Yeah. Is that gonna help us any? No. So this right here is probably the standard deviation, 3.6. That makes sense. Now to read where I got that, I messed up. I'm doubling it in my head, trying to double it, and then I was supposed to double it again, and I forgot to. Yeah. All right, the empirical rule, I think we got about to here. This is about where we stop, so make sure you write this down. Empirical rule is pretty important. The empirical rule is the one that we're going to use the most. We're going to use this throughout the year, sort of. All right, this is just a separate rule, sort of, but the bell curve and being symmetric, that's what we're going to use the most. So as we go over this, even though it might not be in this exact form that we use it throughout the year, it's going to be the same idea throughout the year. I just made up a list of numbers here, 1 through 16. It's not always going to be that way. If we look at that, there's 1, 2, 3, 4, 5, 6, 16 numbers, right? What would be, could anybody guess and tell me what the mean of these numbers are going to be, since I just put them all in order? Going to be probably right there in the middle, right? 8.5 probably. What we're saying with the empirical rule is that about 68% of the data fall within one standard deviation of the mean. So that means if we go out this way, one standard deviation, and we go out this way, one standard deviation, that amount of the numbers should be about 68% of the numbers. Give me a fraction that might make more sense than 68%. What's 68% close to? Yeah, it's about 70%, so 7 out of 10, about 2/3. 2/3 is 67%, right? So what you're saying is either higher or lower, about 2/3 of the data have got to fall within that range of the mean. So anytime you're given data, about 2/3 of it should fall in that range. The next one. 95% lie within 2 standard deviations. So if we went out, whatever our standard deviation is, our S is going to be something like, maybe our S is 3.6 or something. That's what it was on that other one, right? So that's telling us if we take 8.5 and we add 3.6 to it and go up, that's 1 standard deviation to the right. If we subtract 3.6 from it and go down, that's 1 standard deviation to the left. If we went down another 3.6, that would be 2 standard deviations to the left. If If we went up another 3.6, that would be 2 standard deviations to the right. And we're saying about 95% of the data should fall within that range. So this is the empirical rule just says 68% is within 1 standard deviation, 95% of the data is within 2, then 99.7% is within, how many standard deviations do you think? 3. So 99.7% falls within 3 standard deviations. So if our standard deviation was 3.6 and our mean was 8.5, we just take that 8.5 and add 3.6, that's where our first standard deviation is going to fall. Then we add another 3.6, that's where the second one's going to fall. Then we add another 3.6, that's where the third one's going to fall. So on and so on. And it's going to make more sense here in a second when I put up the next slide. But the rule is 68, 95, 99.7. 1 standard deviation, 2 standard deviations, 3 standard deviations. Sean, that make any sense? Mr. Hurd, that make any sense? You sure? Are you lying to me just so I'll leave you alone? Alright, this is more what I want you to write down. Don't write it down yet because I think there's another slide that's better. But this will explain it. 68%. If this is if that right there is our X bar, our mean, we put it right in the middle. 68% of the data is going to be 1 standard deviation below that. So we subtract off the standard deviation, whatever it happens to be, or 1 above it. So 68% of our data is going to fall within that range. Then on the next slide, or it might be this slide, I don't know. They're going to put another one out here. Instead of X bar minus S, guess what this one's going to be? X bar minus 2S. Because then you go down another standard deviation, and up here you go X bar plus 2S. So you add a standard deviation. Then you're going to do the same thing. What do you think this is going to be labeled? Instead of X bar minus 2S, it's going to be X bar minus 3S. This one over here, plus 3S. And we're saying 68% of the data will always fall in here. 2/3 of the data, a little more than 2/3 of the data will always fall in there. 95% will always fall in there. And Grant's probably sitting there going, well, 68 and 95, that adds up to be more than 100. But Grant knows that the 68's inside the 95 already, right? So it's already being counted in there. And then from here to here is going to be 99.7%. Where do you think that other 0.3%'s at? Out here somewhere. What do we call those? Outliers. Those are the outliers. There's going to be 1 or 2 outliers for a set of data. So, and I'm going to go ahead and put this next slide up. This is the slide I want you to draw. Now, when you draw this, don't worry so much about all this stuff up here. You might put, you might draw something and put like 68% there, and then maybe draw something like this and put 95% there, and then draw something to the outer ones. I don't know. Make it so you can understand it. That's a bell curve. Notice, why is it called a bell curve? No guesses? Looks like a bell. Real creative.
Looks like a hill.
So we'll call it the hill curve for you, Jesse. That's fine. Just remind me of that every time we talk about it for the next 6 months.
Really learning this.
Carson, you gotta remind me every time, right? I'll say bell curve for the rest of you. Then for Jesse, I'll say the hill curve. the hill curves. So notice when we get down here what they've actually got it separated. This area right here is 34% of the data. This area, 34% of the data. This area from here to here is about 13.5%. This area is about 13.5%. The little tails out here, about 2.4% on each end. So every time, that's what your bell curve is going to look like, hill curve. And every time, that's about what percentage of the data should fall in those ranges. So from the mean to one standard deviation above should be 34%. So if I was going to do your grades in here, say we did the grades on that last quiz, I'd find the mean and I put that mean right in the middle. Then I put 34% of your grades above that mean right here, 34% below. Then I take the next one and I put 13.5% below here and another 13.5% above here. So on, so on, so on. This is just like our school grades. This is what the school grades actually started off to be, and then they sort of got away from that. This 68% should be what letter grade? C. C's average. All right? So 68% of all grades that are passed out when you get your report card should be a C. 13.5% should be a what? B. And then only about 2.4% of grades should be a A. Then if we go the other way, another 13.5% should be a D. And about 2.4% should be an F. That's what the grades are supposed to be. Because C is supposed to mean what? Average.
Means I'm above average. So I got all A's.
All right, again, the empirical rule, bell curve, just looking down here, I got rid of some of that mess. One standard deviation below, one standard deviation above the mean, the X bar. Two standard deviations above, two standard deviations below. So it's separating that whole bell curve into those sections. 68% should fall in that range. 95% falls in within two standard deviations, so two below or two above. And then about 99.7% falls within all three. And then the other 0.3% is your stuff that's way out here, and those are your outliers. If we were going to do like ACT or SAT score, I know at my son's school, one of his classmates just scored like a 35 on their ACT, which I think is really, really good, isn't it?
That's 1 point away from perfect.
Yeah, or something. And so his grade would probably fall out here. And he didn't just score that. That was last year because he was a sophomore when he scored it. Grant, what are you doing?
On the door.
All right, so a sample of IQs has a symmetric. Remember, symmetric means all symmetric. We wrote this down at one point. Symmetric just means that when you're looking at the graph of it, if we were going to do a histogram, it would look maybe something like this, where it looks symmetric. It looks the same on both sides. So it has a symmetric distribution with a mean of 100. So our X bar is 100. How do I know it's X bar and not sigma? or not sigma, mu, sorry. It's a sample, it tells us sample right there, all right? So, X bar is 100, our S is 15. Sketch the distribution. So this is what we're gonna do, we're gonna sketch that. Somebody write down X bar is 100, S is 15 for me, so that we can sketch this. You're gonna draw this. Got your little bar here. What are we gonna put right in the middle? What goes right in the middle? Look at your little graph. The X bar, what is our X bar? So we're gonna put 100 right there. They told us X bar was 100, so that goes right in the middle. That's our mean. What they tell us S was? 15. So when I wanna go out one standard deviation this way, where am I gonna be at? 115. What if I want to go out another standard deviation that way? 130. Another one? 145. What if I want to go one standard deviation this way? 85. How about another one? 70. And then one more? 55. Now, they wanted us to sketch this. Let me go back, I didn't read the whole problem. They wanted us to sketch the distribution. 68% of the people have IQ between what two values, and we'll answer all those questions here in a minute. But they want us to sketch it. So if we sketch this, our curve's gonna look something like, and when you draw these curves, your curve doesn't have to be perfect. I'm not going to ask you to draw your curve perfect every time, all right? Does that look fairly close? Yeah. Where should 68% of the data fall at on this? 115 to 85. That's 68% should fall in there. So that's our, I think that was the first answer. So between 85 and 115. 68% fall between what two values? 85 to 115. And you should be able to figure that out as you're going through and doing this. What percent of the people have IQ between 70 and 130? So if we go back and look at this, 70 and 130. From here to here, what percent? 95%. 95%. So the answer to this one's going to be 95%. What percent of the people have IQ between 100 and 115? Go back and look at it. Sometimes they make them a little harder. What did it say here? 100 and 115? Yeah, let's make sure. What's wrong with it? Yeah, between 100 and 115. So if we're looking at this from 100 to 115, what percent of the people is going to fall in there? 34%. You got to be able to draw this though. You got to be able to draw that graph. So 34%. What percent of people have an IQ above 145? Above 145. 0 point what? 1. Actually, it's point. It's 0.3 for the two ends, right? How would we find half of that? Divide by 2 is it 1.5? 0.15. I knew what you meant, but if you write that down, I'm going to know what you wrote down too. So it would be about 0.15%, which we know Dalton, that's the range you would fall in, right? That 0.15. So it's like, what that's 0.15 is saying is that Dalton, with his IQ, he falls in that range. Well, out of 100 people, Dalton's not even going to make the score because he's too high. right? So we'd have to go up a little more. Dalton's like 15 out of, so him and 14 other people out of every 10,000 people fall out there, have that high of IQ.
I'm on there too.
Hill.
I figured out a new way to do
All right, in a survey conducted by the National Center of Health Statistics, the sample mean height of women in the United States ages 20 to 29 was 64.3. So that's our X bar. Sample standard deviation was about 2.62 inches. So standard deviation, that's our S. Estimate the percent of women whose heights are between 59.06 and 64.3. If we draw our little curve here again, that looks spectacular. What's going to go right in the middle right here? 64.3. That's your X bar, that's your mean. Then all you're going to do, get your calculators out and help me because I can't do this in my head. 64.3, add 2.62 to that. That means you two, Grant, right there.
66.
I'm going to take it down to the office.
66.92.
Dad has to stop by on his way home to pick it up. Huh? To your dad? Tell him it's his own stupidity then.
I can hold this one.
Have him tell me, because or ask me, I'll tell him.
I can hold Grant's one.
Only I won't be as nice, I'll. 66 point what? I know, Jesse, then you got off track by doing something else. How, if we take off 2.62, what do we get?
64.2.
Now, Jesse, use your calculator. Don't even say an answer if you're not gonna get the calculator out.
61.68.
60 what?
1.68.
That's why I told Jesse not to even use it.
Well, once I thought about it, I seen.
Let's take off another one. Take 61.68 and let's go down another standard deviation.
60.
Jesse.
59.06.
Hey, that's one of the numbers they gave us, wasn't it? Imagine that. And then let's add another one to the 66.92.
69.54.
Now, here's where we got to be careful. They ask us for what percentage of the women would fall between 59.06 and 64.3. If I go out here, does that mean I'm out here, so it's going to be 95%? No, because my other end is right here. What percent of the women fall in this range?
68.
34%, right? What percent falls in this range? 13.5. So about 47.5% should fall in that range. Almost half of the women fall within those heights. So that's what they did. They show us there. We're here and here. Those are the ones we wanted. Add them together, 47.5%. All right, Chevy Chevs theorem. Go ahead and give you a minute. The empirical rule only worked for symmetric data, so data that maybe look like something like that. But Chevy Chevs works for anything. It doesn't have to look like that. It could be skewed left, skewed right, whatever. So it could look, maybe it's data that looks something like this, where it's skewed left, has a tail out to the left or a tail out to the right, but this works for all data. The proportion of any data set line within K standard deviations, K, it has to be greater than 1 of the mean is at least, and then it uses this. So this is, you're looking for the portion, the percent. or it's actually gonna give you a decimal answer, but, so what you do is you do 1 minus 1 over k squared, where k is how many standard deviations you're looking for away from it. So if we're looking for 2 standard deviations away, then you're gonna say 1 minus 1 over 2 squared. Well, what is 2 squared? It's 2 squared. So 1 over 4, what's 1 minus 1/4?
That would be
0.75. So we're saying about 75% of all data should fall within 2 standard deviations of the mean. No matter if it looks like this or if it looks like that. This works for all of them. So K is going to stand for the number of standard deviations that you are away, and you just plug into that little formula. And that's what I just did there, about 75%. We did another one, 3 standard deviations. We're saying that about 89% of the data should fall within 3 standard deviations. Now that would make, if we're, with this one, if we're saying 89%, then all of a sudden Dalton doesn't look quite as smart if we use it on the other one, because now there's, instead of just 0.15% out there on the ends, now there's like 11%, so there's about 5 or 6% out on the ends, so he's now come back to the group a little bit.
It's because I couldn't get the high pass switch on it.
Is that what it was?
Yeah.
Alright, so with Chebyshev's theorem, for data of any distribution, k standard deviations of the mean is always at least 1 minus 1 over k squared. We just wrote all that down. This formula here is all that really matters with Chebyshev's theorem. So not knowing Chebyshev's theorem, not knowing how to pronounce it, that's not going to affect you. So if we're looking at this, they tell us mu this time is 39.2. Remember, that's our mean. And we want to figure out, let's see, the age distribution of Florida is shown in the histogram. Apply Chebyshev's theorem to the data using k as 2. What can we conclude? You got to be able to make these conclusions. That's part of a whole big part of statistics, is being able to say, okay, that tells me this. If that's 39.2, if we want to be within 2 standard deviations of that, then we would do something like, we'd take 1 minus 1 over k squared, or over 2 squared, sorry. We just did all that, that's about 0.75, right? 75%. If we wanted to go in a little deeper, they told us the standard deviation. Well, we could take that standard deviation and draw sort of our bell curve here and say, okay, to be 2 standard deviations down this way or 2 standard deviations up this way, could we find those limits? Grab your calculator out. 39.2, take away 24.8. That's going to put us right here. Now take away another 24.8. It's like -10, isn't it? Somewhere around there. What's that tell us? Are we ever going to go down that far if we're dealing with age? Alright, it's not wrong, but we're never going to go down that far, are we? Because you're not going to have a person on here that has an age of -10. Add 39.2 plus 24.8. That's going to tell us this first mark here. Then add that to it again. What's that going to be, about 88.4 or 88.8? Is that right? So what we're saying is that when we're looking at this, we're saying that 75% of all people who what? Live in Florida. And this is what you got to be able to do. You got to be able to explain this. Live in Florida. What do we know about them? Yeah, give me something a little more meat on it. 75% of all the people who live in Florida are what? Between
-10 and 88.
ages of -10 and 88.8, right? Now, do we really want to write down that -10? No, so 0 to about 89.
The oldest person there is 89.
No, we're saying what percentage?
Oh.
75% of them. So there's other people that live outside that range. Well, we look at this,
I can only be older than 89.
we look at this. Does it look like it's only 75%? It looks like we're almost 100%, right? Because it only goes up to 85 anyway. Actually, it goes up to like 90 right here, probably. So it looks like we're at almost 100% of all the people.
You can't tell me 25% of the population.
Right. And that's why with Chebyshev's theorem, it's not as good as if we could do it symmetrically. If we could deal with it symmetrically, we could get more precise. But with Chebyshev's, using this, it's not the greatest thing ever. But we know for a fact that, or we can say for sure, 75%. But you probably, Jacob, you probably could have done that with just your brain and said, yeah, 75%'s that age or less, because it looks common sense wise, right? Now, other things will not look quite this bad, though. His theorem will be a little closer from a lot of things. So they did the same stuff. They said 75% is between 0 and 88.8, and we rounded ours to 89. I don't know why you put in 88.8 years old. That won't make sense to anybody.
People always say that they're like 12 and a half.
And they don't say 88.8. All right, write this down. Sample standard deviation for frequency distributions. This formula is sort of important. I'm going to explain what it is. We've been doing frequency distributions. Remember, frequency distribution was where we had our x's, then you had your frequency. My pen's not writing very well. And then you had once you had your frequency, we could count all those up, and then we did stuff like relative frequency, cumulative frequency. So this is saying if you have one of these charts where you're doing this, you might have your tally in there. We did tally in there for some of them. Frequency, so on, so on, so on. That's a relative distribution.
Should we write all that?
Hopefully you've got it in your notes somewhere already, because we've done it like 4 or 5 different times now. You might have, on these, you might have your midpoint in there. You might have, there's a bunch of different stuff that you might have in there. You might have your classes, so on, so on. For a sample standard deviation, for a frequency distribution, what this is saying is instead of, when we had this, instead of taking each number separately, like 1, 2, and tallying them all up, if we have one that goes from like 1 to 5, 2 to whatever, so on and so on, if we had it in the classes, if we had classes instead of our x's, then we could use this formula to find the standard deviation. And notice if you look at this right here is just the sum of the squares. That's what we did normally anyway when we made out that other chart that we took the quiz on last time. Speaking of which, Grant, give me that quiz. Talk to me before you take off. F, what's F stand for? Frequency. N stands for the number that you're dealing with, so how many of them there are. And here, since we're doing a sample, we do N minus 1, not just the capital N. Alright, when a frequency distribution has classes, estimate the sample, mean, and standard deviation by using the midpoint of each class. That's why sometimes we put midpoint, because if we go 1 to 5, and you say, well, I don't know what it is here, well then what we do there is we add them together and say, okay, the midpoint there is 3. That's the number we use as our sample mean. So that's the number that we use in there for each one. And probably, I'm going to write this down, this doesn't have anything to do with this problem. We're going to start doing stuff like this. When we do the classes, we did problems that had the classes in it, and you did your frequency and all that stuff. We did midpoint. We're also at some point going to add another thing to this, and that's the class boundaries. Don't make class boundaries harder than they are. Class boundaries, when I was helping my son with his prop stats class a couple nights ago, his teacher wanted him to put the class boundaries in there all the time. If we had this 1, 5, and then 6 to, if we had those as our classes, midpoint, remember midpoint, you just add these two together and divide by 2. So midpoint here would be 3, midpoint here would be 8. Class boundaries look like this, because you want to make sure it includes everything that it could possibly include. So Jesse, listening to this, right? Because this is one of the, and he said everybody in the class had trouble with this, Dad, and it doesn't make sense to me why they do. All you're going to do here to make sure it includes 1 and it includes 5 is you're going to go backwards half of a unit, and you're going to go forwards half a unit to make your class boundaries. So for our class boundaries here, it'd be from 0.5 to 5.5. What would it be for this one? 5.5 to 10.5. Don't make class boundaries harder than they are. Now, in our set of numbers, like this set of numbers right here, are we ever going to have a 0.5 in there? No. And the purpose of the class boundaries, Dalton, is so that it's all inclusive. Because if we go here, if we just do 1 to 5 and 6 to 10, then somebody looks at this and they say, well, where's 5.7 at in there? Well, it's not in our set, so we have to be, to make it so it's all inclusive, it includes every possible number, we need those class boundaries, because then it goes from here to there, then it stops there and goes up to there, even though those numbers are never going to fall in there. Does that make sense?
Yeah.
So somebody, somebody like Jesse back there would try to be a smart aleck. Well, what if it was 5.7? That's not on the list. And then we'd have to.
I don't do that.
You never do anything like that, just in a hill. You collect a random sample of number of children per household in a region. Find the sample mean and the sample standard deviation of the data set. Because Jacob's getting tired of hearing me talk. If we had to find the sample mean, we'd add them all up, divide by how many of them there are, which is 50. Sample standard deviation, we'd use the formula. I'm just going to let this, it shows us the answer here, I'm sure. First, construct frequency distribution. So we got our frequency distribution here, 0, 1, 2, 3, all the way up to 6. There was 10 of those, 19 of those, 7, 7, 2, 1, so on, so on. Then what we have to make, and this is where the chart's going to start to get a little longer. So you got your X, you got your frequencies, then you're going to take X times F. The sample mean is about 1.8. So what we do with all that, we got X times F on this. We come down here. We add all those up. We get 91. How are we going to use that 91 to get our sample, our 1.8 here? What'd they do to it? Yeah, they should. Yeah, it does look like they should have done it, because they were doing a sample. So they got 1.8. I don't. Maybe not there. Maybe that's just in that when you're finding standard deviation. All right. So when we're just finding the x bar, we still just divide by the number. All right, because we're just finding the mean. So we're saying the mean of all of this is about 1.8. The sample mean of all those numbers that they gave us is about 1.8. Notice here, and why they do this, I have no idea, because right after this, I still think that you ought to leave in that x times f. You ought to have that column in here. So you might want to write down this right here, and I'm going to stop. Then we take that, and you got to go back to your formula. And now is where we're going to use, Sean, now is where we're going to use the n minus 1. So you go back to the formula. We just found this. That was 145.40. And now we're going to stick in n minus 1, which was 50 minus 1. Do all the math there, and you come out with about 1.7. So your standard deviation is about 1.7 children. I didn't even read what this question was asking. Was it talking about children per household or something? You collect random sample of number of children per household in a region. So they're saying, all right, you went around each house, and one house said they had one person or one child, next one 3, so on, so on, so on. Some of them, you know, got 6, 4, whatever. And then the sample standard deviation that we came up with was about 1. Let's see, let's go through this real quick. Somebody remember that 1.8 for me? If we were to, if this actually fit a bell curve, our mean would be 1.8. We put that right in the middle. One standard deviation this way, one standard deviation this way. What's 1.8 minus 1.7? 0.1, right? Now look, does this would be 3.5 going up this way. Is this really going to work with this set of data? No, because as soon as we get down here, some of the households are going to have negative 1.6, and we're only 2 standard deviations away from the mean. Might work up this way. 2 standard deviations would be about 5.5. So if we're looking at that, it's not actually going to be symmetric, because it's going to be the other way, right? It's going to more people are going to fall that way than down in the negative range, because it doesn't fit for negative kids. You don't, but we're saying the standard deviation. So the average household is going to be, the average household has 1.8, right? And that's not possible, but that's the average. So we're saying that if we went out to New Paris and looked around, that about 2 would be the number of kids per household. It's not ever going to come out exactly a whole number, because you're dealing with a bunch of different numbers. You know, somebody could have 0, somebody next one have 2, so on and so on.
Ronald Landis has like 15.
All right, coefficient of variation. This is the last thing. So write this down. Just write down this. Coefficient of variation. Let me see. Describe standard deviation. Data as a percent of the mean. Can use to compare 2 sets of data with different units. Might write down that. population data set. And this should say 100% right here. I don't know what that little extra box is. Make sure you write down that formula. That should say 100%. Again, I don't know what that little box is. Make sure you write down that formula. So this is for a population, this is for a sample. What this coefficient of variation tells us is it sort of tells us how good our standard deviation is. Nick, would it be better if I rewrote those? So our CV equals, what's that again? Sigma, what's it mean? Standard deviation for the population, right? Over mu times 100%. And then, so this is for a population. Our coefficient of variation for a sample is S over X bar times 100%. This is for a sample. I'll be out of the way in 1 second. Just look at what I just wrote up here instead of looking at those. I'm not sure where that box came from, something crazy that the PowerPoint doesn't like on the slide, so it sticks in something extra. Again, the coefficient of variation is sort of a way to decide whether you're, or a way that you can compare your two things, two different sets of data. So maybe like on that one problem we did on the homework the one day, we had males and females. Well, then we could better compare the two if we use the coefficient of variation. Shows population of heights, so it shows heights and weights of a basketball team. So if we looked at this with our heights and weights of a basketball team, can you really compare a person's height and their weight? Sort of, but not really. So what the coefficient of variation does is allows us to compare those two, even though they're two completely different measurements. Find the coefficient of variation. We take our coefficient of variation, we take our sigma, which was, they told us was 3.3. We take our mu, which was 72.8. Divide that and you get 45%. That's for the heights, or 4.5%, sorry. 4.5%. Then we do the same thing. Do the same thing for the weights, about 9.4%. Do what? Yeah, well, when you do this, when you divide these two, it's going to give you a decimal, and then times it by 100 is actually just changing it to a percentage. So the weights are 9.4%. The heights are 4.5, so we compare those two, and apparently our basketball team is a bunch of chunkies or something, because their weights vary a lot more than their heights. That doesn't mean our whole basketball team. It means that we probably have, you know, those two basketball players that are like 6'4" or something, but they weigh like 270. Seen teams like that before, right? Where they have that one great big guy that stands out there in the middle and does this, and
What about the one that's like 5'2"?
doesn't move. Yeah, well, he usually doesn't get on the court, though. He usually sits over on the sideline. Yeah, go ahead and write this down. I forgot about this. Pearson's index. Pearson's index of skewness tells you how something is skewed. If I can move this. Pearson Index of Skewedness. So this P stands for Pearson. I'm not sure if this Pearson's the same guys that wrote the book or not. Probably is, because they like to mention, might be his dad or something. They like to mention Pearson's statistic rules all the way through the book, which sometimes they're alright, sometimes they're not much to them. So Pearson's Index, you just take 3 times X bar minus the median over S, which is your standard deviation. And you need to write down all of this, because this is how you're going to use Pearson's Index. It's going to tell you whether the data is skewed left, skewed right, or symmetric. So if you go through and you find Pearson's Index number and it comes up to be something like P is negative 1 point, stupid thing. P is negative 1.8. Well, we look at this, and if the P is less than 0, then that tells us it's going to be skewed left. Remember, skewed left, and I'll draw little pictures here so that you can have it. If you have data and it's skewed right, it's going to look something like that. If you have data and it's skewed left, it's going to look something like that, where it has a tail going to the right or a tail going to the left. If it's symmetric, then it's going to look something more like that. It's going to look like the bell curve hill. He's lost back here. So skewed right, skewed left, symmetric. Most all distributions should be between -3 and 3. We already talked about that with the bell curve. Riley, did you have all that? I'm sorry, do I need to go back? I don't know why I left that on there. So we covered all that. I'm not going to go back over that. That's your assignment. Why is that stuff staying on there now?